coefficients. Exponential, Fourier, the first thing you do, you find DC. The DC C0, that'll be easier. Some of them, in this case, DC is the integral over one period, 0 to t, of the area of xt. Area of xt over a period. And then divide that by period to average it. So you need to find out what the period is. T, the period is equals to, a lot of people still don't know how to do this. The period, you just look at the diagram here, and then you see the period. So the waveform repeats every 4 seconds. So that's the period. So in the exam, you have to show all these things. Therefore, omega is going to be 2 pi over the period. Omega naught one over t, 0 to t. For DC, okay. So we don't need period for DC. I mean, yeah, we need period, but we don't need the frequency for period. We just need the period. Period is 0 to 4. One over t, 0 to 4. 1 over 4. 0 to 4. That's a period. But you must understand that the signal only exists up to t equals 2. From 2 to 4, there's no signal. Right? So the period is from year to year. But however, there's no signal here, 0 signals here. There's the signal amplitude over here is 2. Signal amplitude is 2. The signal amplitude is 1. So from 0 to 1, the signal amplitude is 2. And then from 1 to 2, the signal amplitude is 1 to 2, the signal amplitude is 1. So that's how you calculate your DC. T 0 to 1. Either you can integrate this individually, or another way to do this is just to find the area. Find this area, and then there's another area. Since this geometry is rectangle and square, so you can, instead of integrating, you also can use the most basic area formula for rectangle or square. which is just the length times breadth, right? So the area from 0 to 1 is 1 times 2. One times 2 plus the area from 1 to 2 is the blue shaded region. It's going to be 1 times 1. Okay, you can only do this if you know the area. The geometry is very clear to you. This is a rectangle and a square, so it's too easy to figure out. But if it's not clear to you how the geometry looks like, then you have to integrate this. Okay. So 1 over 4 multiplied by 2 plus 1. So that's a DC. Any question?
No, sir.
Okay, next we find the Fourier coefficients using the formula. So we are able to find it for DC, but if you want to find the Fourier coefficients, then for non-DC, then you have to use the formula 1 over T, 0 to T, e to the xt, e to the negative j, and omega naught t. Which is going to be 1 over 4. Of course, then again, the area you have two different areas. One of them is amplitude 2, e to the j, and omega naught we calculated earlier to be pi over 2. And the other area is dt plus 1 e to the j and pi over 2t. So here we cannot simply go and find the area by looking at the square and rectangle, because we have an additional term here, exponential terms. That's what we can do. We can split the integral quarter, just multiply the 1/4 through, to multiply this 1 by 1 here. So 1/4 multiplied by 2 is 1/2 e to the minus j and pi over t. And then the other one would be, forgot to put the integral signs. Forgot to put the integral sign. Nobody corrected me. Okay, let me do this again. Otherwise, I have problem editing later. So it's going to be 1 over 4. Okay, and then open parentheses, and then integral from 0 to 1, amplitude 2, j and omega naught t dt plus So 1 to 2, amplitude 1. So next, if we multiply this through, okay, and then you get 1/2 e to the minus jn. Omega naught is pi over 2. We calculated that earlier. Then the integral dt plus quarter times 1 is 1/4 integral e to the minus jn pi over 2 t dt. So now we integrate 1 over 2 integral of exponent. You know how to do, right? So when you integrate the exponent, is 1 over minus j and pi over 2. Divide by the differentiation, the derivative of the exponent, and then and pi over t. And then similarly, on the other side, is 1 over 4, 1 over j and pi over 2, which is a j and pi over 2. Of course, you know, we have to integrate this. Let me put the limit of integral. So this integral goes from t is equals to 0 to 1, and this integral here goes from t is equals to 1 to 2. So what you can do is you can pull out the common factor. Or you can just keep it. It's okay. Don't try not to simplify too much for now. Okay, then see right here you have pi over 2 here, and you have 1 over 2, and that's 1 over 2 here, and these two can cancel each other, correct? And then here also you have 1/4 here, and then if you flip this around, and then it will become 2 over 4. So this is going to be minus 1 over j and pi e to the minus j and pi pi over 2 upper limit, which is 1, minus the lower limit, which is 0, close parentheses. The second part is 1/4, 2 over 4, it becomes 1/4, so 1 over 2, minus 1 over 2 j and pi, and then plug in the upper limit. There's a plus here, so e minus j and pi over t times by 2 minus e to the minus j and pi over 2, 1. So it's going to be minus 1 over j and pi. minus jn pi over 2 minus e to the 0 is 1 minus 1 over 2 jn pi over 2 times 2 at the exponent. The 2's will cancel, and then you're going to get minus jn pi minus e and pi over 2. Okay. Now you can open the parentheses. Open the parentheses. So you will get 1 over jn pi e to the minus jn pi over 2 plus 1 over jn pi. You know, you can, of course, you can simplify things without going through all these things, but you have to be very careful you don't make any sign errors. That's why it's a good idea to go through all the steps. Try not to avoid doing the algebra in your mind. Okay, this is what you get. So like for this part here, you can combine these two. These two you can combine, right? Sorry, you cannot combine those two. You can combine perhaps these two because they have the same exponent. So you might be able to, should be able to combine these two. Okay. Okay, if you combine those two, what do you get? Minus 1 over jn pi plus 1 over 2 jn pi. If you multiply by 2 top and bottom, you know, if you just multiply these 2 by 2 top and bottom, and then you will get minus 1 over jn pi. Okay, jn pi. Okay. Okay, so you have to try to carefully multiply them out, and then if you possible, you try to simplify things. Okay, are you guys still there? Let me check.
Yes, sir.
Okay.
In, sir.
Okay.
Sir,
The
first one supposed to be minus 1 over 2 jm pi, am I right?
Which one?
The first, minus 1 over 2 jm pi, is it? Because
The
minus
first
1
one.
plus, yeah.
Oh yeah, I forgot. Yes, that's a mistake here. 2. Okay. You mean this one?
The final answer. The final answer, minus 1 over 2 jm pi.
Okay, let me. Okay. The final should be
minus 1 over 2j and pi.
for this part, yeah. You mean for this one? This one, yeah.
Yes, sir.
Okay. I think so, yeah. There's some computing error in my mind. Thank you. Okay, thanks. Good job. Is that right? You guys agree?
Yes, sir.
Yes, sir.
It looks like I messed up. There's a negative sign here. I forgot the negative sign. So if I combine those two, you get minus 1 over 2j and pi. Okay, let's continue. Okay, now let's look for opportunity to simplify this further. And we know from last time that e to the minus j and pi is minus 1 to the power of n. I mean, it's not necessary. How you get this is because using the Euler, this is cosine n pi minus j sin n to the minus j sin n pi. Okay, sin n pi is always 0. Multiple of pi sine is always doing a 0 crossing. So this is always 0. So we have just cosine n pi. And cosine, multiple of cosine pi is always negative 1. No, it's alternating. Not always negative 1, because this is cosine. So cosine pi is here. Okay. After when it's 2 pi is positive 1. So it's alternating. For odd number is negative. For even number is positive. It's 1 minus 1. For even multiple pi is 1. For odd multiple pi, say cosine x or something, or cosine n pi or something. For odd multiple of n, cosine is 1. So this can be for even multiple. So you can try yourself. You see, when you put n equals to 1, 3, 5, and so on, it gives you minus 1. When you put 2, 4, when you let n even, like 2, 4, 6, and so on, you get positive 1. Don't really have to do this, but you can just leave it the way as it is. Okay, well. It's minus 1 over. Okay, later on when you do programming in MATLAB, it becomes easier for you if you simplify things. What about the odd multiple of pi over 2? We don't know that yet, so I think that also is cosine. Okay, let me plus 1 over j n pi minus, so you can replace the everything here, that 1 over 2 j n pi. So you can replace minus 1 to the power of n. Okay. So let's see whether we can simplify this or not. I'm just trying, you know, let's see. This can be, if you use Euler, it can be cosine n pi over 2 minus j n j sine n pi over 2 cosine pi over 2. You can see from there, multiple pi over 2 is going to be always 0. Cosine, let's say, if we look at cosine, if we look at the cosine here, pi over 2 is 0. And then 3 pi over 2 is also 0. So you also multiple pi over 2, this is going to be 0. Multiple pi over 2, so this is 0 minus j. Because sine multiple pi over 2 is always 1, isn't it? Let's see, I think it's not 1. It's going to be alternating. For sine pi over 2, sine pi over 2, this is just for fun, you know, I'm doing. Actually, just find out yourself. So this is sine pi over 2, and then next pi over 2, multiple pi over 2 is 3 pi over 2, and you see the sign is alternating. Okay, it's alternating. Can you guys see the sign is alternating?
Yes, sir.
When n equals to 1, and then when n equals to 2, when n equals to 2 is pi. Sorry, pi sign is 0. At pi sign is 0. When n equals to 3, so it's alternating between 1, 0, minus 1. So it's complicated, you know. So we cannot replace that with in a more compact form, correct? So in that way, it's not worth it to try to simplify it, because it's alternating between 0, minus 1, and plus 1. So we just leave it as it is. Then now next we try to pull out the j and pi. I mean, all this will help you when you do the programming. 1 over j and pi. Pull out, you get 1. And pulling this out, pulling this one out, so you get 1 minus 1 half minus 1 to the power of n, and then minus 1 half e to the Okay, this is the Cn. And then this is the C0. This is the exponential Fourier series coefficients. We cannot have n equal to 0 here because we have a division by 0. So you see, we cannot have a division by 0. That's why we calculate the DC separately. In this equation, n cannot be 0. Xt, then you put them all together, complex exponential Fourier series minus infinity to positive infinity, Cn, E, J, and pi over 2, T. Of course, you also have DC. This is going to be DC 304 plus n is not equal to 0. So this is a complete complex exponential Fourier series. Complex exponential Fourier series has a DC part, and then it has the AC part, which is composed of the Fourier coefficients. Okay, the Fourier coefficients. And now don't forget, we forgot to put this here. It's supposed to be here, right? So this is the equation that you need to program into MATLAB to plot this. Okay, this is the equation, complete equation that you need. So you can see this last time, remember when we did the assignment 1, when we were doing assignment 1, like this was F0, isn't it? We call this F0. And then we call this Fn. Here we're calling this Cn. You can use Fn or F0 if you like. This is from a previous problem. They were using C, so I was just using C, but you also can use. So what you need to do now, we have to, what this is doing, what this equation is doing, it is trying to synthesize, it's trying to synthesize this waveform. So we can put this in a Fourier series. Whatever you derived here, it's written in the program now. So what happens now, in this case, like this n here, it's actually little n equal to 3. That means n equals to a DC plus 1, 2, and 3. So here n is equals to 1, 2, 3 up to 10. So as you increase the n, what happens is you improve the accuracy of the wave, the plot. Like when n equals to 3, your plot is actually doing this. Your plot looks like this, right? Like this, isn't it? Sorry. Your plot looks like this. Something is, isn't it? Something like this. And then you had but because the number of n that you are using is only 3, you are not able to completely reproduce the waveform. But as you increase the n, like in this case, n is just 3. N is 3. In this case, n is equals to 10. As you increase the number of n, as n increases, you'll be able to reproduce the waveform more accurately. Now you're getting there, you see, right there. Almost. But still, there are some ripples. As you increase n further, and n equals to 40, you get a more accurate representation of the original waveform. But still, as you can see, there's still some ripple here. So this is what you call the truncated Fourier series, when n is truncated to 3, and this n is truncated to 10, and this one in this, the n is truncated to 40. The program has been done for you. There are also many other examples. The program, you see, the program is giving you the period, and this is the frequency, 2 pi over period. And this t is telling you, you start when t equal to 0, and then you increase t by a step size of 4. T over 1,000 here is 4 over 1,000. That means you're increasing 0 plus 4 over 1,000. 4 over 1,000 is how much? 0.004, right? 0.00004. Okay, and the next step will be 0 plus, the next step will be 0.004 plus 0.004. And then next one will be 0.008. So you keep increasing the step until you reach the endpoint, which is 3 times the period, 3 times 4 in this case. So you start at 0, you keep increasing the step. The smaller the step, the better the resolution, until you reach a step of, final value for the time is 12 seconds. 4 times 3, 3 times 4 is 12 seconds. So this is the program is just, and then the end post, I really don't know what that is, but you can always figure it out. You just can, DC is here. I myself, I'm not sure, I'm not really very good in math lab. I know just a little bit. Some of them I understand. Some of them I don't understand, but still I don't care. Because all you need is just 1/4 of the understanding to be able to do this problem. You can just leave it there and just only change some things. So in this problem, you don't really have to change few things like this. Maybe you don't have to change. Maybe the DC part you change. The DC that you're going to get when I give you a new waveform, and again you get a new DC, so you change this. Maybe then you have to change this. Like this is the new Fourier coefficient that you're going to be deriving. You only change these 2 things. Is that difficult to do? I gave the lab to the other guys, and then a lot of people got almost 0. So this is one example. You also can use other programs. So what I would like you to do in this lab, so you'll be given, you know what I would like you to do, you repeat the same thing that was given to you. So maybe you are given a square wave. You're given a square wave. Okay, this square wave, maybe let's say this is 5, and then this is -5. Call this amplitude, you know, amplitude 5. And this is, let's say this is called this your xt. This is time. And this is one period from here. Let's say you're going from 0, 2, 4, 6, 8, and 10. So your period is going to be t. T is in this case is 4. If I do a small offset here, let's say if I'm doing okay, let's say if I'm doing an offset, a DC offset. Okay, let me do this continuously so that I can show this. I'm sorry about that, you know, messed up drawing. So I'm doing an offset. Let's say if I take it, do a little bit of offset. Now you already moved the offset. This is the offset. So this is the offset. Let's call this offset, OFF, is equals to +1. So you're moving the entire curve by 1. And then this is going to be, let's say if you move it by 1, and then this is going to be -4 here. Let's say if I move it down, to say if I move it down, the entire waveform offset by -1. So you're going to come like this. So it's going to be 4 here, and then it's going to be -6 here. Okay. So that's one change. Then it's possible that, let's say, if I also can change the period. See, if I change the period, change the period. So now the period is shorter period. Period is t equal to 2 now. So in this lab, what you're supposed to do, each one of you should have a different period. What is your period? And then what is your amplitude? And then what is your offset? Okay, each one of you must have an offset. You know, you cannot have something centered at the zero. Must have an offset. So you guys go and derive the Fourier for each different period. So no one should have same period, amplitude, and offset. Okay, at least one of them should be different. If anyone have the same thing, so later on I would like you guys to send me a WhatsApp and tell me what period you choose, what amplitude you choose, and what offset you choose. Then after that you find C naught. And then also find the Fourier series coefficients, and then write xt C naught plus minus infinity to positive infinity xt. What was the formula? See, right here, Cn Fourier coefficients e to the minus jn pi over 2. I think the negative infinity, positive infinity, this part here, I think. Something to do negative infinity, positive infinity, n is. But there are also other ways to plot these things. I don't, there may be other programs you might be able to find in the internet. You can go to the toolbox and then you just do the same thing. I would like you to plot when n equals to 3, when n equals to 10, when n equals to 40. Plot when n equals to 3, n equals to 10, and n equals to 40. Okay. Lab 2. Due on Arun. It's a 2-sentence collab report, just an objective statement. Objective, let's say, for example, you know, don't copy mine. Objective is to learn how to derive, learn. Just I'm just writing something. You just write what you feel like doing. You say learn how to derive. Hey, what's that noise? How to derive and program Fourier coefficients. Derive for exponential Fourier series coefficients. Learn to derive, learn to derive exponential Fourier series coefficient and program and plot and program and plot in MATLAB. Plot truncated Fourier series in MATLAB. Something like this. I don't want too much things. I don't want too much fancy stuff. Here, then you put in the derivation, your end calculation, show everything, your calculation that you calculate xt with the diagram, nice diagram. Show me your square wave, your offset, your period, everything. A, T, what else? A, T, N. Yeah, you get a brain jam. A, T, N.
Offset.
Amplitude. Offset. Good. Offset. Just show it and then you derive it. Find xt. That means you just find xn. Find c naught and then find an xn. Sorry, xt. Cn. xt. C naught plus after giving so much details, still some people won't do it. I don't know why they are doing it. I just have no idea. Probably they vowed to take it again. I don't know. I'm just guessing. So after doing this, and then your program, MATLAB program code, and then your plot. And then make a small conclusion. Actually, no need conclusion in this case, just plot. You want to make a conclusion, conclusion is optional. But there's no mark. You can just say as n increases, as n increases, xt the waveform becomes the plot. As n increases, the plot approaches the original waveform. Approaches the original waveform, something like this. Just write what you think in conclusion.